Okay, so our next speaker is Dr. Pete Shadbolt, co-founder and chief scientific officer at PsiQuantum. PsiQuantum is a quantum computing company. Their mission is to build the world's first commercially useful quantum computer. PsiQuantum approach to building a large-scale fault-tolerant quantum computer involves a photonic-based architecture and enable manufacturing in a conventional silicon chip foundry. After earning his PhD in experimental photonic and quantum computing from the University of Bristol in 2014, Dr. Shadbolt was a postdoc at Imperial College researching the theory of photonic quantum computing. During his time at Bristol, he demonstrated the first ever variational quantum eigensolver. He has been awarded with the European Physics Society's prize and the 2014 EPSRC Rising Star by the British Research Council. The EPSRC stands for Recognizing Inspirational Scientists and Engineers Award. Please welcome Steve. Thank you.
Thank you so much. It's a real privilege to be here at this wonderful conference. I'm Pete. I'm a co-founder of PsiQuantum. And today I'm just going to tell you principally about work that the company is doing towards a large-scale quantum computer, and also try to put that work in context. I want to start with this image. This is a favorite image of mine. It's a picture of a black hole, and you can see the accretion disk and the event horizon. If you've seen the movie Interstellar, you might recognize this kind of fairly scientifically accurate picture of a black hole. This is a special image because it was made in 1979 on an IBM punch card-based mainframe computer. And of course, those machines back then didn't have a display. So a reasonable question is, how was this image made? This was made by a French gentleman, Jean-Pierre Lumière. He took a big canvas, he took a paintbrush and India ink, and spent presumably a very long time feeding punch cards into the computer, getting numbers out, and painting individual data points onto the canvas to form this image. And I think it must have been an amazing experience to see this beautiful, accurate picture appear. I like this because it's a testament to the power of seemingly primitive computers, and it is also, to me, a metaphor for quantum computing. There are many people in this room, Joe and David and many, many others, who've spent their entire lives in pursuit of a useful quantum computer. Myself, my co-founder and CEO, Jeremy, has been in this field 25 years. And quantum computing still continues to have this insane gravitational pull on thousands of our best scientists and engineers and billions of dollars of capital. It's pretty crazy to see. I think there's a good analogy with machine learning. Of course, the wave of excitement that we've seen around AI recently is the product of entire fields of research, thousands of people, decades of work. But I also think there's a strong case that it was really just a few papers quite recently that ended up swinging billions of dollars of capital and creating the world's most valuable company. And I think there are similar sort of dynamics at play in quantum computing, where, of course, that field emerges from quantum physics and information theory and the work of thousands of people. But it's also the case that it was really just a few papers, 1995, 1996, and 1997, that ended up swinging billions of dollars of capital and putting thousands of people on a lifetime journey. That journey has taken us here. In my personal view, this is still the most impressive quantum computer that exists. That's my opinion, not the opinion of the company, but I think this is the best one. And it really is amazing, right, to see a single chip that can unequivocally win a race with $1 billion supercomputer. That's something that I waited a decade of my career to see, and there's no question that this system is unbelievably impressive. It is also heartening to see that the leaders of these organizations, who some might sometimes worry would be detached from reality, they're not. They actually understand that you're going to need much bigger systems on the order of 1 million qubits, and you're going to need full error correction and fault tolerance if you want to do anything commercially useful or actually valuable with these machines. Not only do they understand that they need much bigger systems, they're actually starting to do something about it. And I think it's quite exciting if you read between the lines of these images from Google, IBM, and others. People are taking tentative steps towards building data center-sized, million-qubit, fault-tolerant quantum computers. That has been the singular mission of our organization for the last 8 years since we were founded. to realize a large-scale fault-tolerant machine. The approach that we take is based on photons, so putting light into a chip, and we start with the microscopic components that you see on the left here. So these are integrated photonic components that we essentially borrow from the telecom industry and that allow us to move single photons around on a chip. Most of these components are fairly conventional, but there are some exceptions, like the superconducting single photon detector that we use to detect single particles of light. Those components go onto a chip using the material stack that you see here. Those chips go into a package that we hope to mass manufacture in a similar sort of way to cell phones or optical transceivers that you find in data centers. And then we're going to need many thousands of those packages to give us a 1,000,000-qubit quantum computer. So those packages get racked up into cryogenic cabinets that you see in the fourth column here. Those cabinets are cooling the chip to liquid helium temperature, deep space, 4 Kelvin, and that's to support the operation of the superconducting detector. And we're going to need on the order of 100 of those cabinets to give us a useful machine. So that ends up with a data center-like facility that you see on the right. To give you a feeling for where we are in this picture, we have made and tested tens of millions of devices. We've made thousands of wafers of silicon. We've made hundreds of these board-level assemblies. We have one cabinet running in the UK that's a sort of prototype size system, and we're now setting up full-size cabinets at the Stanford Linear Accelerator. I'm going to take a tour of work that the company is doing from left to right in this figure, starting with the microscopic things and heading to the macroscopic things. As far as the microscopic devices, a big part of our thesis was that if we want to reliably manufacture millions to billions of devices that all need to perform beyond the state of the art, there are very few places on planet Earth where you can actually do that. This is GlobalFoundries in upstate New York. It's a commercial semiconductor foundry in the same category as TSMC, Samsung, and Intel. And it still kind of blows my mind that we make millions of superconducting detectors, millions of quantum devices in this factory, and we've been doing that for 4 or 5 years now. So shoulder to shoulder with chips that go into laptops and cell phones. Here you can see those wafers, and if you were to look inside those wafers, you would find these microscopic devices that are described in the paper reference that you see at the bottom. So starting from the left, we make silicon waveguides that carry telecom band photons. We make thermal heaters that we use for fairly janky, slow control of the chip. We make superconducting single photon detectors that can detect photons with very high efficiency. And then on the right, an ultra-low loss silicon nitride waveguide and a barium titanate phase shifter, which we use for fast control of the photon. Now, when we started the company, we knew that we would need to make all of these devices way beyond the state of the art. So better than Cisco or Intel or any of your photonics companies, better than the national labs, better than the universities. We had to achieve really far and away state-of-the-art performance on all of these components. When we set these targets for our teams, you can imagine that some of our engineers were up in arms and denouncing their leadership as deranged because these were such aggressive component performance targets. And it's been really amazing to see the team track exponential curves for 3 or 4 years running in the performance of these components. In some cases, we're now significantly exceeding the targets that we originally set for fault tolerance. In some cases, we're not quite there yet. But overall, I think this is a very encouraging picture for the execution of our team, and also for the premise that these components are going to be at spec before the large-scale infrastructure for the machine could be ready. And I'll say more about that large-scale infrastructure in a second. We've taken those components and built qubits, interconnects, 2-photon interference, and 2-qubit gates. Now, it's interesting in these chips, those thermal heaters, when we turn them on, get to a few hundred degrees Celsius. So they're actually many times above boiling point of water, but they are millimeters away from superconducting detectors that are at 2 Kelvin. We also have a laser shining into the chip that is 1 trillion times more intense than the photon that we detect. That's the same dynamic range as the difference between a ship-mounted US Navy laser weapon and the most distant star visible to the human eye. And so we have insane optical dynamic range, crazy thermodynamic range. You might imagine that that would lead to lots of noise and bad performance of our qubits. The good news is that we actually see pretty good performance on these qubits, competitive, I think, with other things that you'll see from other platforms. The only caveat here is that these numbers don't account for loss. That is because they were measured in a silicon platform where the waveguide loss is too high. We've since spent the last 4 years introducing silicon nitride waveguides into the platform. Here you can see 4 years of hard grind by the team to produce silicon nitride waveguides that are now exceeding the target spec for fault tolerance. And it's very sort of comforting to know that we're building those devices in a commercial semiconductor foundry where the expectation is that when you place an order for wafers, they all basically work. And so here you can see the uniformity of our splitters and our crossings. We can't do this in a small fab. We can't do this in a university clean room. This is why we spend so much money to go to a big, expensive commercial foundry, is this uniformity and predictability. We've recently swapped out our superconducting detector for a new design that can now count the number of photons in the waveguide and increases our efficiency to about 98.9% median on-chip efficiency. We've introduced a completely new class of single photon source that is tolerant to manufacturing imperfections and achieves very high purity, as well as world record coincidence to accidentals ratio. And there has been one big elephant in the room for photonics, which is determinism. So in a photonic quantum computer, we have a lot of work to do to overcome non-determinism. And for that, we need a very high-performance optical switch, better than anything that you can buy from the telecom industry. To solve this problem, we resorted to a new material. We built this tool. This is the biggest molecular beam epitaxy tool in the world, to our knowledge. It's a dual-chamber 300mm MBE tool, and it makes wafers of barium titanate, which is the strongest electro-optic material known to science. We're the only people in the world who do this. And we make it clean enough that we can then take those wafers out of this tool and integrate them into a high-volume commercial semiconductor foundry. So there's a huge risk for the company to take. And the good news is that that risk has paid off. We're now making essentially perfect wafers of this switching material, at 1,000 picometer per volt, few percent uniformity. And we have taken those wafers and integrated them together with a 35-layer silicon nitride process from GlobalFoundries, allowing us to make up to 64-port switches now. To put that number in context, the biggest switch that we ever plan to make for our first-generation system is about a 128-port switch. So we're not quite there, but the complexity of these chips is now getting into the ballpark of the chips that we will mass manufacture for that first-generation system. That switch has really been the key to allow us to then start to climb up this ladder of increasingly complex subsystems that sits on our roadmap, going from entangled state generation to resource state generation to a full high-performance logical qubit, and then finally to an actual computer. As we start to step up that scaling path, we're going to run into needing more cryogenic cooling power. And so this chandelier on the left, which has become the kind of icon of quantum computing, that only fits 1 or 2 chips, and it's very limited in terms of the heat dissipation that can be achieved. So a few years ago, we set out a plan to get away from the chandelier and move to a new category of cryostat that achieves much higher density, so we can pack lots of chips into one cryostat, and also achieves orders of magnitude more cooling power. When our team started showing me 3D renders like this, I said, you guys have gotten really good at Blender. But, you know, when a team comes and says, we're going to commandeer a couple of abandoned synchrotron accelerators, and we're going to build a completely new class of cryostat, and here are the 3D renders, you're understandably a little skeptical that they're actually going to do this. I was really gratified to see the team go and execute on that. So this is a decommissioned synchrotron accelerator in the north of England. It has a liquid helium cryoplant that makes the helium that we needed to test this. This is PsiQube. This was our first non-chandelier cryostat. Still very much a development vehicle, too small, not dense enough, but it was designed to achieve 10 watts of cooling power at 2.3 Kelvin. It's doing about 20 watts of cooling power. You can see here an array of chips inside the cryostat. To put that number in context, if you're at 10 millikelvin, as is the case for a superconducting qubit, you need a dilution refrigerator. The biggest still fridge in the world is at Fermilab. It achieves about 1 milliwatt of cooling power at 10 millikelvin. So this fridge is doing about 20,000 times more cooling power than the biggest still fridge in the world. And that's just by virtue of operating a few degrees higher temperature. That fridge is, as I said, a development vehicle. So we've been busy building bigger fridges. And you can kind of get a feeling for how this is going to be laid out. There are shelves, essentially, inside this cryostat that will carry as many chip packages as we can fit inside the cryostat. And you can also get a feeling this is a different kind of engineering to the very delicate Swiss watchmaking style that we normally associate with quantum computing. This is a big, ugly piece of stainless steel fabrication. It's actually built by a company that normally does contract manufacturing for the pharmaceutical and food and beverage industries. It is also going to take a lot of helium. Where are we going to get that helium from? This is the Stanford Linear Accelerator. It's walking distance from my house. And this is the SLAC LCLS2 cryoplant that makes 36 kilowatts of cooling power at 4 Kelvin. So these are the compressors and turbines and cold boxes that make a ton of helium that then gets pumped into the LINAC. This is the same kind of scale of cryoplant that we will build in Australia and also here in Illinois. And we're very grateful to the Department of Energy and to Stanford for letting us tap off a little bit of their helium and use it to actually test those cryostats. Now, when I show large infrastructure like that, it's not very impressive to my dad, who's a wastewater engineer, and apologies to high energy physics colleagues, but he wasn't impressed. He said, I've seen stuff much bigger than that in my life. But it is impressive to me as a former physicist working on an optics bench. This is big stuff. The helpful sort of reference point that I got to see recently is at Aurora. So this is at Argonne National Lab. This is the second fastest supercomputer in the world. And of course, when they show you the supercomputer, they show these beautiful renders. It looks very clean and nice. What they don't show you is what's underneath in the subfloor, which is the liquid cooling system that actually is not very far removed in terms of the scale of industrial machinery required to cool these systems. So it was very heartening, actually, to see this in real life. I was very happy to take some of my architecture colleagues who spend their entire time in front of MATLAB to see this stuff. And we're very grateful also to the teams at Argonne and Fermilab who have experience with this kind of high-power cryogenics, large-scale systems. So here you can see that MK1 cryostat plumbed in at the Stanford Linear Accelerator. I think actually just in the last couple of days, the team have been working until 3 o'clock, 4 o'clock in the morning, and they now have this system cold. So that has been a huge effort by our team to get that installed, get it running. That will start loading thousands of single photon sources into that cryostat as soon as we can, and then the plan is that DARPA will actually come and scrutinize this system starting in 2025. You can also see from these images that we're going to run out of space in that building at SLAC, and I'll say more about that in a second. I've been made to show this video to put that in context. This is a wafer. We've split the wafer up into chips. You can see here an array of single photon sources. We actually put a lot more sources on the chip than you see here in the long run. Those chips get packaged together with ASICs that we design and build. They emit photons into fiber there. You can see the gold cold plate at the back there that's at 4 Kelvin, and then feed-throughs on the front where fiber and electronics are attached. We're basically going to need to mass manufacture those blades, and then we're going to put as many of those blades as we can fit into a big cryostat like this. That's basically the same kind of magnitude as what we're building at SLAC. And then in our future systems, the task is really to scale that up, build a large number of those cabinets, and network them together with optical fiber. Here you can see one of the blades that's now under construction at PsiQuantum, still work in progress, but you can see the 4 feed-throughs on the front. So those are vacuum feed-throughs that you could kind of see reflected, if I can go back. So you can actually see the array of feed-throughs on the front of the cryostat here. Those correspond to the feed-throughs that you see in this blade image. So we're going to run out of space, and a few years ago we started looking for sites where we would go ahead and actually build a very large machine. And so this is a picture of my co-founder and CEO, Jeremy, together with Ambassador Kennedy Minister Husic, the Prime Minister of Australia, the Premier of Queensland, and the Chief Scientist of Australia, announcing that we're going to build our first utility-scale machine in Australia, just outside the Brisbane airport. You can see the site on the right-hand side here. And then, sort of hot on the heels of that announcement, we started looking at a site here in Illinois. This is the US Steel site on the south side of Chicago. It used to make 1 million tons of steel a year, an industrial behemoth, engine of the war effort, and so on, and a site that has sat empty for 40 years. And we are extremely privileged and excited to be now planning to occupy that site and start to build hardware on that land, alongside, of course, other quantum computing companies, startups, university research groups, national labs, etc., and of course DARPA, as you heard from Joe earlier. So it's a huge privilege to have this opportunity, and we are working very hard to prepare to break ground on that site. It's also really exciting to be doing that in a space that has a history of eye-wateringly ambitious engineering challenges. So reversing the flow of the Chicago River, lifting entire city blocks off of the ground. And I met somebody recently who casually announced that they are putting 70,000 tons of liquid argon under the ground like it was breakfast cereal. And to be surrounded by people like that is very, very welcome, given the magnitude of what we're trying to do. So just to take a step back, there will be people in this room who will remember when AI and machine learning was a completely failing field. And there have been times in the history of the field where you wouldn't even admit to being an AI researcher, because there had been so many failed promises, it was taking so long, and there was widespread doubt over the viability of that field. Here's the Lighthill debate back in 1973. DARPA actually defunded AI at some point in its journey. And you know, of course, they're basically making it, I think it's fair to say, like they're making it out of the dark. And a good fraction, in my view, of the reason that they managed to do that was not just borrowing someone else's hardware in the form of video game chips, but also in sustained, extremely sort of challenging, sustained exponential progress in the reduction of resources required for machine learning architectures and algorithms. And so this is data from OpenAI showing about 7 years of sustained exponential progress, just reducing the resources required to implement these machine learning algorithms through cleverer schemes. Here's an even stronger example, in my view, 20 years of similar progress in mixed integer programming. So this is basically just mathematicians, people with pencil and paper, coming up with cleverer and cleverer and cleverer schemes and reducing the resources by a huge fraction. And we have to do the same in quantum computing if we're going to make these machines useful and if we're going to fit useful applications into those systems. The good news is that we do actually have similar kind of trajectories, exponential progress over about a decade here in improving the resources required for these applications. Not only do we have the historical data, but we have at least one round of making predictions and then actually being able to hit those predictions and follow that trajectory. But we're far from done here. There is still a long way to go. So you can hopefully get a feeling for the sort of breadth of what the company is doing. We do work all the way from the angstrom to the kilometer and everything in between. We hire oil and gas people, aerospace people, semiconductor people, theorists in quantum error correction, quantum information, algorithms, very, very, very broad scope. We need a lot of help to get this thing to work. The only thing that's off limits, I think, is probably the commercial fab. It's going to take a long time to build one of those in Illinois. I hope they do. We're covered on that with Global Foundries. Everything else basically is on the table, and we would be really excited to hear from people who want to collaborate on any of these topics. I'll skip over that slide. And then just to wrap up, I can come back to that if people are interested. I appreciate I'm between people and lunch. I just want to make the point that when we arrived in Palo Alto 7, 8 years ago, we moved our lives and families to California to start the company. it's not as if we had some grand plan of who we were going to collaborate with, which businesses we were going to work with, which supply chains we were going to set up. We had no plan at all. But we came with a very sort of ambitious activity. And here you can see a map of the supply chain that we have in the Bay Area, and similarly here in the US. And so over the years, we've ended up finding the best partners, the best suppliers, the best academic groups who we can work with. And we're very excited to have a similar kind of blast radius here in Illinois. So obviously, I don't do any of this work. I just make the PowerPoint. It's a huge privilege for me to present the work of my colleagues here. Great pleasure to speak at this conference. So thanks for the time.
Well, you're a great PowerPoint operator.
Thank you.
That's actually very fantastic. What is your funding model? You mentioned government funding, so do you get venture capital funding? Could you just say a little bit? And also the rate at which it comes in, because it sounds like you have to make big investments at some point,
Yeah.
and then there's time to implement it. But something about the funding model, please.
Certainly. So my three co-founders are university professors. They have left their positions, but they were university professors for 15, 20 years before we started the company. So the four of us worked together in the university in the UK for combined 60 years or so. That was publicly funded work. Once we founded the company, then we were almost exclusively privately funded to this point. So we've raised just over $700 million in private venture capital. And then at this recent juncture, then we've started to take public money. And so in Australia, there's $1 billion Australian associated with that deal for us to build a machine in Brisbane.
Thanks for the nice talk. One question. Correct me if I'm wrong. You're quite unique compared to other companies in the fact that I believe there is not yet any prototype available for accessing to run algorithms and so on.
Yeah.
Is there a particular reason for that? And do you have a roadmap for when researchers or the user community will be able to evaluate the machine you're building?
Yeah, so we don't have a small quantum computer that we put online and let people play around with that system. There are two fundamental reasons for that. The first is that we don't want to do that. And secondly, it wouldn't be very good even if we did. So let me unpack that. I had what I think is probably the first quantum processor of any kind on the internet a decade ago. So we took chips that we had at Bristol, we gave them a web API. This was when we were in the university. You could play around with that system. 2-qubit system. It was actually the thing that we used for the first demo of VQE. And we thought that was a fun, sort of community-spirited thing to do back before we started the company. We've always positioned ourselves with investors, governments, etc., that what we're not going to do is take venture capital and turn it into papers. And we're also not going to take venture capital and turn it into demos that are academically interesting. What we're going to do is take all of the resources that we have available to us and go as fast as humanly possible towards the machine that is actually worth money, the machine that is actually useful. Now, the caveat there is that if you're an outside observer, that's frustrating. I understand the frustration. How can we judge where you guys are at if you don't have a 5-qubit processor with an API or something? The answer is to come and talk to us or to work with us. And DARPA is working with us. They will scrutinize that system in depth next year. And many other people work with us and see what we're doing. And I think the company has a reputation for secrecy. That's primarily because we haven't spent a lot of time going to conferences, publishing papers, and being sort of academic adjacent. However, if you come and talk to us, we'll be absolutely delighted to show you where we're at on component performance, where we're at on systems integration, and you can get a feeling for the state of the technology. But I think there is a deep sort of risk where this field can keep producing breakthroughs forever. You guys know every week there's a breakthrough in quantum computing, and there's a press release, and there's an excited journalist, and so on. And we could have continued doing that for another 20 years, and we would not have bothered to go to a big commercial fab. We wouldn't have bothered to go and find large sites where we can actually build systems, because that's got nothing to do with making an interesting demonstration. So I appreciate it is an ideologically confronting approach, but we think we're doing that for good reason.
So one question I have here is, I think the photon loss is probably the thing that everybody is most skeptical about. Can you just tell us a little bit about the journey that you took? What are the technology bets? How optimistic you are in the future? But also tell us some of the human aspects, because I'm sure that was very controversial, both outside, but also internally.
Yeah, so I mean, so on photon loss, like what do we actually do? We've probably spent $50 million just making wafers where each wafer is a tiny, tiny bit better than the last one we made, and they all go in the trash. And there's nothing quantum going on. There's nothing that the editor at Nature would be interested in. It's just pure grind to improve the material quality, the lithography, the design of the extremely mundane passive optic components. And you spoke to the human component. Of course, a lot of those people, when we first hired them, they said, oh, can we publish papers? And they said, oh, can we do a demo? And it takes like a serious effort to say, no, you may not. You must spend the next 4 years of your life just staring at a curve that boringly, slowly goes down, thanks to late nights and hard work and a ton of capital. And so, yeah, it has taken a concerted effort to create a culture of people who think that way and who have, as you've seen, improved losses in these photonic devices well beyond the state of the art, well beyond what even global foundries could achieve themselves, et cetera. And I'm very proud of the team for kind of staring at that coal face and just continuing to chip away and not getting distracted along that journey. And I don't think we're unique in that. I think that pretty well every quantum computing platform has some kind of very hard engineering challenge like that, which isn't going to get solved except for with a very long grind. And so, yeah, we have cultivated a team of people who understand why that is a good use of resources.
Hello.
Yeah, please.
My question is pertaining how not necessarily, I wouldn't call it a culture of secrecy, but how do you balance that with the trade-off that academic institutions do not know exactly how the progress is made and how they can train the workforce so that that workforce helps you in the long run? It's hinting at the fact that if you don't necessarily connect with people or hide it, I understand the trade-off of we're wasting resources that are not going into creating the fabrication conditions. But the workforce also wants to know how we can be of help to you so that we can get to that fault-tolerant computer faster and know what skills we need in terms of developing ourselves as professionals.
Yeah, it's a really good question. And I think what I'd say is we work with lots of universities. Like we have lots of academic collaborations. We have collaborations with national labs. We have collaborations with small quantum computing companies, hardware vendors, etc. And so it's all super possible. And I hope you also see, like from what I'm presenting here, and you can come and talk to me afterwards, like there's very little that we won't tell you about what we're doing. There are tiny pieces where, whatever, it's really difficult to talk about, but the vast majority of the work that we do, if you talk to our researchers, if you talk to me, if you talk to the team, we'll tell you a lot about what we're doing. We just, there's so much distraction associated with then twisting that and contorting it into the thing that appeals to the editor at Nature or that is going to go down really well at a quantum computing conference or whatever. And it takes your best researchers to do that. It takes your best team members to go and do that work. And so I know we're sort of contrarian and and annoying about this, but it is a heartfelt sentiment. And then as far as like how do those collaborations get established, the best collaborations from what I've seen are always based on genuine need. Like we actually need something and someone else can actually make it for us now. Not like, you know, it would be nice one day to use this device and that's an interesting thing to think about. But like the most straightforward things to get done are either like we want to evaluate it or we actually need to use it in something that we're building next year or the year after that. And those collaborations work really, really well and everyone's really happy. And it's a little painful when it's like, oh, we're both doing quantum stuff. You know, we should really find a way to work together. That's always just kind of painful in the end from what I've seen. So I think it's about identifying the real need and just a very simple transactional relationship between two organizations. That, from what I've seen, is the most successful when we work with universities, national labs, etc. Yeah.